Hey, this is Matt. And so today we're going to be talking about the RSA algorithm. And this is part one of a two-part video. And so part one will be talking about generating keys. This is part of the cryptography on simple cipher series, where we actually go and look at the mathematics behind each of the simple ciphers. So just a few things looking at the history of this is it was actually developed in 1977 by Ron Rivest, Adi Shamir, and Lynn Aldman. And it in the RSA algorithm actually creates the public and the private key. So when people hear of public and private keys, the first thing that they think of is encrypting data across the internet, which, yes, it does this. And it also does quite a bit more, which, speaking of this, Professor Don Patterson does a great job with his video, and I will post a link to that. Uh, there, there's a software engineer in Vancouver that does a fantastic job with his paper website on on RSA as well, which Professor Don Patterson, he actually goes through asymmetric key encryption and goes a lot deeper into it. So I will also post a mod checker so you can double check and make sure that your calculations are correct. And a greatest common divisor calculator, I'll post a link to that. And there's the extended Euclidean algorithm, which we'll be touching on just a little bit um, in this tutorial, but I will post a link to a calculator and a video that does include that as well. So, with the algorithms that are included with the RSA algorithm, which is basically made up of two, it is comparing that to what we have been talking about mostly within this series. It's not the most simple one. I mean, most of them we've talked about are very easy, like a rotating cipher, you add 13 or subtract 13, and it basically encrypts and decrypts itself. A Caesar cipher, you take the letter, the character, the letter that is presented as ciphertext or as unencrypted text, and you add or take away that number. With, say, a veneer cipher, we're going to take the table and we have a keyword and the text, and you basically match it up on the X and Y. This one requires a lot more math behind it, and for good reason that it's very complicated, because this is used, once again, to encrypt data across the internet. So, looking at some of these algorithms, we've got how do we encrypt the data? And that is C equals m to the power of E mod n. And we're going to be going over what the variables actually mean coming up here in just a second. But to decrypt it, because having the encrypted text without being able to decrypt it is pretty useless. So it doesn't help. So to decrypt it, we've got m equals c to the power of d mod n. So what do all these mean? Well, C is ciphertext. U would be the unencrypted message or the decrypted. Uh, D would be the Euclidean D, and this is used to decrypt the text. So think D, decrypt. Now, decrypting, we're going to apply that to the private key, because you don't want your private key going out for everybody to be able to decrypt your messages. So that's private. Now, because we've got a private key, we need a public key. So E is the greatest common divisor of the coprime and phi n. So you start off with picking E as a coprime, and then you then put them together, calculate the greatest common divisor, change it if necessary, and it is the coprime, and it is used to encrypt the text. So that will be with your private key. Now, because we've got phi n, we need to be able to calculate phi n. So we've got p minus 1 multiplied by q minus 1. So that is how we get that. We've got a multiplied n, which will be used with both your public and your private key, and we'll see that here in just a moment. We've got prime p, prime q, and we have a constant value, or constant variable, however you want to say it, but that will be k. And we'll show how to actually calculate that here in just a moment. We've talked a lot about public and private keys. Whenever we hear public and private keys, we think of Alice and Bob. Now, this has been confusing in the past to some, so the simple way to explain this is that this whole thing started is Bob wants to send a message to Alice. Well, Bob doesn't want everybody on the internet to know what he's sending to her. So what he does is he calls her up and says, hey, I'm going to send you a message. I need you to send me a key or some form, some way to actually encrypt this data. So what Alice does is she has a public and private key calculated out, generated, which is what we're going to do. And she gives him the public key so that he can encrypt the data. So the public key is E, comma, N. So E stands for encrypt, which that is your coprime, and that it's the GCD coprime, comma, phi n, and that's used to encrypt the data. And then we have private key, which is used to decrypt the data, which is D, which will be the Euclidean D, comma, N. Now, the N for both of these is the multiplied N. I called it that for a reason, and you'll see why coming up here in just a moment. But first, we need to pick a number, and not just any number. Let's pick a prime number. You can pick one, anyone. And keep in mind, this is not an exhausted list. I would highly advise that at going through this tutorial that you would pick the same numbers that I do. If you choose to pick something else, that's more power to you. You're welcome to, but it's going to be a tad tougher to follow along with the video if it's not exactly lining up. So pick P and Q. So these are used to generate the public and the private key. Most of the time, well, if not all the time, these are randomly generated values, and they use a true random number generator. And these are much larger normally than what we're going to use today. However, for testing purposes, I want to use some small values because most of the time you guys know that I do this by writing the program to actually, y'all can see how it goes through from point A to point B and it flows. This one you'll see where I actually ran into some issues given the data type not being able to decrypt it because of the length of the value. So, but you'll see that coming up here in just a moment. So I chose 17 for P, and for Q, I chose 11. So because we have just these two values now picked and chosen, we can now calculate two of the main variables we need, which is multiplied n and phi n. So you multiply them together, that's why I called it multiplied n, or this is just n whenever you look at the public and the private key, and that's 187. Now for phi n, it's p minus 1, q minus 1, multiply both of those together, and you get 160. Please feel free to follow along, do the math yourself. Because I did not have this written as a program and then ran into some issues, I was able to get it all the way through on the encryption, but I went ahead and have done all this by hand, showing you how it all works together and fits. And then I triple checked it. So, but please follow along so that you can practice yourself. So choosing a coprime. This is one of the other variables used to encrypt it. This is the other part of the public key. We need to choose one, and because we now have phi n, we can actually check the criteria. Now you can choose whatever coprime you want. However, it's got to meet, must be coprime to phi n, and it's got to be lower than phi n. So I chose the number 7, which is definitely lower than phi n, and we can check it does meet the criteria of the greatest common divisor equals 1, so 1 is less than our chosen value, and it's definitely lower than phi n, so it does meet the criteria. So we can set E or coprime equal to 7. So finding the public key, we need 2 variables to be able to meet this. So we've got E and n, coprime and multiplied n, and we get 7, 187. Now, we can publicly share this. It's having the encrypted text, and having the public key. It's very difficult and very time consuming to be able to calculate and bring it all the way back to decrypted text. In fact, during part of this series, it's going to move from just simple ciphers to quantum, and I may start a brand new series on that, but we're going to actually be looking at Shor's algorithm and how that will be used to actually decrypt this RSA algorithm. But for right now, just rest assured that your information is fairly safe going back and forth. So now we need to choose a constant. So going through, we pick K. This would be calculated using this algorithm. A would be phi n, B would be E, which we've figured that is. So A is 160, B would be 7, and our final result would be K equaling to 1. And most of the tutorial videos and such that I've seen have been, and some of the programs even, have just said, well, you can just pick whatever value you want for K. That does work a lot of the time, but most of the time, just follow through with your actual, or you can even use algebra to take it back once we show you the actual algorithm. But I would highly advise that you actually calculate this out. So calculating the Euclidean D. So D is defined as e to the power of -1 mod phi n. Now e we know as 7 and phi n we know as 160. So we can write this as d times e equals 1 plus k multiplied by phi n. Now we've got d. We still don't know d yet. We know e, so that's 7 equaling 1 plus 1 times 160. Well, we can go through, we've calculated out that 1 times 160, well, 1 times anything is itself, so that's 160 plus 1. You guys can obviously do that yourself. Looking at the factors of 160, because now we need to work on the other side, so that is, we can divide that, so you would get 23, or you can just look at the factors and then trial and error. It's whatever, but either way, your D equals 23. And that is now where we can calculate the private key. So we've got multiplied n, and which would be 187, and we have d, or the Euclidean d, is 23. This would be private key is d comma n. So n would be used for both of them. Keep that in mind. That's very important. And this would be 23 comma 187, and this is not shared. This is used to decrypt your message. You don't want to share this. If you're sharing it, then anybody can decrypt the message. So please keep that in mind. Be very careful with that. So just to review, because this is a two-part video, we've got two main algorithms. We've got the one to encrypt the data, which is C equals m to the power of e mod n. And to decrypt the data, we have C to the power of d mod n. And just to look at, we've got our public key, which is e comma n, which is 7 comma 187. And then we have our private key, which is d comma n, which is 23 and 187. So this is part one. This is the end of generating a key, or keys in this case. And so part two, we're actually going to look at the encryption and the decryption of a message. So we're going to see what Bob is actually sending to Alice, and we're going to see how that is actually broken down and converted, as most of the encryption is, to ASCII decimal, then converted through. We can even look at how to decrypt it as well. So thank you very much for your time. If you have any questions about this video, just let me know. Put that in the comments below. If you're wanting more ciphers broken, if you need help with any, let me know. We can also either message me or put it in the comments below. But thank you very much for your time. I really appreciate it. I will have those details in the description below. Those those videos posted down in those details. So if you, once again, thank you very much for your time, and y'all have a good one.